The next thing we're going to speak about here is recruitment. And so again, tying back into this idea that not all muscle fibers are contracting when a muscle contracts, at least not initially, we can speak about recruitment, which is basically stimulating or calling on additional muscle fibers in order to increase how much force this muscle is generating. So just going back to the anatomy here, we know that a muscle is really a bundle of muscle fascicles. Within those fascicles, we've got, individual muscle fibers. And so the more fibers that are actively contracting, that are actively undergoing cross-bridge cycling, the more tension that we will produce. And so recruitment happens at the level of a motor unit. So essentially, we can recruit one motor neuron and all of the fibers that it's innervating. And then we can recruit another motor neuron and we'll then likewise recruit all of the fibers that that motor neuron is innervating, and we will then stimulate or generate all of the force that each of those individual fibers are producing. All right, so here's a little bit of an illustration which shows what recruitment looks like. So basically we start off with motor unit X, and motor unit X is a smaller motor unit. It's got 5 fibers attached to it. And so when we stimulate motor unit X, we're going to generate, let's say, a smaller amount of tension here. If we stimulate motor unit Y alone, we'll generate slightly more tension. But if we recruit both of these motor units together, we're then going to generate, a combined amount of force that each of these units are generating individually. And so that's what recruitment is, calling on more fibers to then generate more force by adding the amount of force that those motor units are producing individually. So let's talk here about, kind of the way that recruitment happens. So we recruit motor units. We said that the more fibers contracting, meaning more cross-bridge cycling, that's going to translate to greater force or greater tension. And so we can activate our motor neurons and then activate all of the fibers that are attached to those motor neurons, i.e. a motor unit. And if we increase that in this kind of stepwise, fashion, then we will likewise increase how much force a muscle generates. And if you think back to more of a practical example, if I'm lifting, again, something heavy, I'm going to try to lift it for a short period of time. Let's say I've started out with 1 or 2 motor units contracting. And then in order to generate more force, because I've realized that this is a heavier object, my muscles are then going to recruit additional motor units to generate some more force so that I can potentially, lift that heavier object. We start off with smaller motor units, so muscles that are attached to more delicate movements like extraocular muscles of the eyes, lumbricals of the fingers, and lumbricals of the toes. We recruit those smaller motor units first. And then we recruit larger motor units, which are usually attached to muscles for strength. So think about, gastrocnemius, your gluteus maximus, your hamstrings, your quads. Those more, bulky muscles for strength are going to be attached to larger motor units, and they will be recruited later on. So we also want to think about the correlation between the size of a motor unit and the type of movement that that muscle is doing. So again, smaller motor units are usually more fine touch, delicate movements. Larger motor units are going to be strength, sometimes also stability. So some of those erector muscles of the back, right, they're going to be recruited as a part of larger motor units. We can also think about the fiber diameter. This varies with motor units as well. So the diameter of small motor units for weak movement is going to be smaller. And then the diameter of larger motor units for stronger movements are going to be smaller. And when we talk about diameter here, we're talking about the fiber diameter, so the size of that muscle itself. We can also think about the size of the axon, like the size of the motor neuron itself. So again, smaller motor units are going to have smaller fibers, but then they're also going to have smaller neurons themselves, so smaller cell bodies and smaller axon diameter as well. So we're thinking about not only the fiber diameter, the size of that muscle fiber itself, but also the axon diameter, the size of the neurons attached to that motor unit. And likewise, large motor units are attached to larger fibers, so bigger muscles, as well as they have, bigger cell bodies in the neuron and then larger or thicker axon diameters. And just to compare two neurons that I'm sure you've seen here, if we look at a small neuron that innervates the extraocular muscles, right? One of our cranial nerves, actually, those are really tiny fibers, really small neurons. The muscle fibers themselves are also small. The diameter of those neurons are small. The somas and cell bodies of those neurons are small. And we can compare that to really large muscles. Look at the hamstrings, right? Larger muscles, the fibers of those muscles are smaller. They've got larger axons. Look at the sciatic nerve, it's really thick. It's also got a larger soma or cell body. And so we want to, make the association that smaller motor units for smaller movements, delicate movements, have smaller neurons and smaller axon diameters. And just on a bit of a tangent here, I got a really interesting question in lab. So a student wanted to know what is the difference between a neuron and a nerve. And I thought that was an interesting question. And I thought I'd bring it to the larger class. A neuron is really the functional unit of the nervous system. So it's one single structure. And a nerve is the bundle of axons only. Okay, so a neuron has the soma or cell body, and that's going to be in the central nervous system, so in the brain or spinal cord. That's where the soma resides. And what we're seeing as the nerve is really only the bundle of axons, and there are many axons within that nerve. So just to make some distinction here between what a neuron is, that functional unit, and then a nerve really is only the axonic projections that travel out to their, their muscle, the skin, wherever it's innervating. Okay. So let's talk about the size principle here. And the size principle is really tying all those factors together. So we recruit smaller motor units first, okay? And that only makes sense. Small motor units are easier to depolarize, whereas large neurons are harder to depolarize. They're going to require more synaptic input, so more of an action potential, more neurotransmitter, a larger amount of vesicles with neurotransmitter. It's just going to require more synaptic energy to depolarize a larger neuron than it would to depolarize a small neuron. And so just as a measure of efficiency, we start by recruiting our smaller motor units first, and then we recruit our larger motor units. And again, thinking about a practical example here, I'm going to recruit, if I'm trying to lift something heavy, I'm going to start by recruiting smaller motor units that have smaller fibers. So again, if I'm trying to lift something with my biceps, I'm going to go for the smaller units that have less fibers. Those fibers have a smaller diameter. The somas and cell bodies of those neurons are going to be slightly smaller. And then the axon diameters of those neurons are also going to be smaller. And I'm going to recruit that first before I go to my larger muscles with larger numbers of fibers attached, larger size of each of those fibers, attached, larger size of the cell bodies and somas on those motor neurons, and then larger axon diameters altogether. So kind of tying all those factors that we talked about together, we recruit smaller first and then larger later on as a measure of efficiency. And this schematic kind of shows that here. So we've got this small motor unit X, it's got less fibers. The fibers themselves are smaller. The cell body is going to be smaller. And then the axon diameter will also be smaller. And then I will recruit last my larger motor unit, which has a lot of fibers attached, so more fibers attached. The fibers themselves are bigger. The somas here are also bigger, and then the diameter of the axon will also be larger. And then the graph here, the small graph at the bottom shows how that recruiting happens. So I'll start with my smaller fibers. Now they're not going to stop producing tension, because remember, I'm trying to increase my overall tension production. And so they're going to keep producing their tension, but I'm going to just keep adding on medium motor units until I get to my larger motor units, which will generate the most amount of force lastly. Okay. I'm going to pause here and see what questions you may have. We've said quite a bit, so let me pause here before we get into the velocity of shortening. Okay. All right, and so the last thing we'll speak about here is the velocity of shortening, and velocity is the rate of muscle shortening or muscle contraction. And so we can think about a muscle contracting isotonically. And when we compare the amount of load that that muscle is lifting, we see that during a muscle contraction, so the latent period of shortening is going to increase as the load increases. And if we think about that again, practically that makes sense, right? The latent period we said was the time for the warming up of the machinery to produce those cross-bridge cycles and allow, force generation. And so as the load gets heavier, the amount of time that it takes for that warming up to happen is also going to increase. So the latent period is going to increase as the load itself increases. We also see that the duration of shortening will decrease as the load increases. And the duration of shortening is how long we can sustain that muscle contraction. And that is going to go down as the size of the load goes up. And again, thinking back to a practical example here, if I'm lifting something that's quite light, I can hold it up for a longer period of time. Like I can stand with maybe a book, or a phone in my hand for an hour. If it were a really heavy item, I would not be able to maintain that duration of contraction for as long as I would for a lighter item. So as the load increases, the duration, how long we can keep the contraction going, will decrease. And then the velocity of shortening will decrease with the increasing load. And the velocity is how fast that shortening can take place. And so likewise, the amount of time I'm going to take to warm up the machinery and to get the contraction, done, if it's a lighter load, will be less than the amount of time I'll take for that to happen for a heavier or a larger load. And another practical example here, if I'm lifting an empty box, I can do it pretty quickly, right? If that box is full of books, it's going to take me a little bit more time. And so the velocity is going to, progressively decrease until there becomes a time where the velocity is zero because the load is too heavy for me to physically lift. So when the load is zero, the velocity is at its maximum. In other words, I can lift an empty box really quickly. I can lift nothing the fastest, right? If I have got nothing in my hand, I can shorten my muscles the fastest. And then as the load increases, the velocity goes down until there's a point where the load is too heavy to be lifted and the velocity is zero. All right, so the velocity will get to zero when the load is at its maximum. And this graph here kind of gives a summary of all of those factors. And so we can compare a zero load graph to a heavy load graph. And what we're looking at is the distance shortened versus time. And the slope of this curve is actually going to be the velocity of the shortening or the rate of the shortening, how fast it'll happen. And if we look at lifting zero load, or we can think about it more practically as being a very light load, the latent period is pretty much zero. So it takes no time to warm up for this to happen. So latent period is zero. The duration of shortening is the largest. So I can maintain or sustain, I can keep this contraction going for quite a while. And then the speed or the velocity with which I can, make this contraction happen is also going to be the fastest. And we can see that by a more linear curve, which is representing the velocity of the shortening. We can compare that to an intermediate load where we've got a longer duration in terms of the latent period. We've got a shorter duration in terms of how long that contraction can be sustained. And then we've got an even more, horizontal graph here. The slope of the graph is going to take a little bit more time in terms of the velocity of that shortening. And then comparing that to a heavy load, we see a larger latent period. So this is going to take the most time to warm up the machinery here. The duration is going to be the shortest. So if it's a really heavy load, I'm not going to be able to sustain it as long as I would be able to sustain the contraction of zero load or a lighter load. And then the slope is also going to be even more horizontal because it's going to take more time. And so the velocity of shortening is going to increase as well.